All right, let's jump right in. Today, we're jumping deep on a very specific but incredibly powerful statistical tool, Mood's median test. Now, if you've ever had to make a call based on data that's being skewed by some crazy outliers, you know how misleading a simple average can be. This explainer is your guide to cutting through that noise and getting to the real story. So here's how we're going to break this down, consultant style, totally Mies. First, we'll nail down the exact problem we're trying to solve. Then, we'll introduce the tool itself, our non-parametric solution. We'll cover the rules of the road for using it, and then I'll walk you through the exact 6-step process. We'll even run through a real-world example, and then we'll get to the most important part, how to turn that statistical result into a smart business insight. Let's get started.
Okay, section 1. Let's frame the problem. You've seen this a million times, right? You're comparing performance across different groups. Maybe it's sales teams, marketing campaigns, whatever, and you need to know if there's a real difference. But the problem is, your data is a mess. It's got some extreme values that just don't play by the rules.
And that really brings us to the core question, doesn't it? What do you do when a few huge numbers are dragging your averages up, or a few terrible ones are pulling them down? If you just compare the means, you could be making a decision based on a complete illusion. One massive sale could make a team look like superstars when they're not. So, how do you find the truth in the data? Well, that brings us to the answer. To get a clear signal, we need a tool that's basically immune to those wild swings. We need something called a non-parametric test. And the specific tool for this job? It's Mood's median test. So, what is this thing? Simply put, it's a test that looks at the median, the true middle value of your groups. Remember, the median doesn't care about a $1 billion sale or a $0 sale at the fringes. It just looks at that 50th percentile mark. It's stable. And this test asks a very simple question. Is it likely that these different groups actually come from populations that share the exact same middle point? Now, if you're familiar with your stats toolkit, here's the easiest way to think about it. You've probably heard of a one-way ANOVA, which compares the means of different groups. Well, you could think of Mood's test as the ANOVA for medians. It does a similar job, but it focuses on the median, which is exactly what we need when our data is skewed. Now, a great analyst knows it's not just about having a tool, it's about knowing exactly when to use it. And look at this. Mood's test has a very specific niche. Sure, something like a Kruskal-Wallis test might be more powerful in general, but Mood's test shines in one key area. It is incredibly robust against outliers, especially when you don't have a ton of data. It's a specialist tool for a specialist job. Okay, so before we just fire up this test, we have to understand the rules of engagement. Like any good statistical tool, Mood's median test has a few key assumptions that have to be met. Get these wrong, and your results could be worthless. So first off, your data points have to be independent. One measurement can't influence another. Second, the data should be continuous. And third, and this one is really important, the underlying shape of the data distributions for all your groups needs to be roughly the same. See, this test is designed to spot a difference in the location of the median, not a difference in the overall shape or spread of the data. All right, we've covered the what and the why. Now let's get into the how. Section 4 is our step-by-step blueprint for running this test perfectly every single time. The process itself is actually pretty elegant. First, you just pool all your data together from all the groups and find one single grand median. That number is your benchmark. Then, you go back to your original groups, and for each one, you just count how many data points are above that benchmark and how many are at or below it. You organize those counts into a simple table, and then, here's the clever bit, you run a chi-square test to see if the pattern you see is statistically different from what you'd expect if all the medians were the same. Finally, you just compare your result to a threshold and make the call. Let's see how it works. Okay, time to make this real. We're going to apply this blueprint to a straightforward business problem so you can see exactly how these steps play out. So here's the scenario. A big agricultural supplier is testing two new crop growing methods. We'll call them Method A and Method B. They've gathered yield data from a bunch of different plots. The big question is one of these methods actually better than the other, or is there really no significant difference in the median crop yield they produce? Okay, step 1. We have to ignore the fact that there's a Method A and a Method B for just a moment. We take all 28 of those data points, toss them into one big pile, sort them from smallest to largest, and find the one number that's sitting right in the middle. And for this data set, that number is 15. That's it. 15 is now our line in the sand. It's the benchmark that we're going to measure everything else against for the rest of the test. And this table right here, this is the heart of the test. It's so simple. All we've done is go back to our original groups and ask for each data point, is it bigger than 15
or is it 15 or less? For method A, we had 8 above and 6 below. For method B, 5 above and 9 below. Now, they look a little different, but is that difference big enough to matter, or could it just be random noise?
So, before we get our answer, we have to state our default assumption. It's called the null hypothesis. We start by assuming that the two methods are the same, that there's no real difference in their median yields. Our test is designed to see if we have enough evidence to challenge that assumption.
And here's the moment of truth. We run the numbers, and our chi-square test gives us a value of 0.86. Think of that number as the strength of the difference signal in our data. We then compare it to the critical value, which is 3.841. The critical value is like the high jump bar. To be statistically significant, our signal has to clear that bar. So, did 0.86 clear 3.841? Nope, not even close. Our calculated value is way smaller than the critical value. So, in the language of statistics, we failed to reject the null hypothesis. In plain English, we just don't have enough evidence to say that there's a real difference between these two crop methods.
But hang on, we are not done yet. In fact, this is the most critical part of the whole process. A statistical finding is not a business recommendation. Section 6 is all about that analyst nuance. What does failing to reject actually mean for our decision-making?
This quote right here says it all. Read it again. We did not prove that the null hypothesis is true. All we did was show that we don't have strong evidence against it. This is such a critical distinction to make. We haven't proven the methods are the same. We've only failed to prove they are different. Let's just put this side by side to make it crystal clear. What we can say is this. Based on our data, there is not enough statistical evidence to say the medians are different. What we cannot say is, we have proven the medians are the same. See the difference? The absence of evidence is not the same thing as evidence of absence. And that leaves us with the final, big picture question. This is where you, the analyst, have to earn your paycheck. When is no evidence of a difference good enough to act? If method B is way cheaper or faster to implement, does this result give you the green light to choose it? That's where the numbers stop and the strategic thinking has to begin.